Okay, the topic this time is relativity. And as we'll see, relativity is not just a branch of physics. It's a principle that all of physics is affected by. It's a real revolutionary change in our way of looking at some of the underpinnings of physics. So, it's a revolution. Let's begin. The story really starts with Galileo. Galileo, of course, was very involved in the controversies about the Copernican system, whether the Earth was at the center of the universe, or the Sun was at the center of the universe, and the Earth went around it. And one of the main objections to the Copernican system of the universe was that if the Earth were moving at incredible speeds through space, wouldn't we feel it? Wouldn't we know it? Wouldn't we be able to perceive directly the motion of the Earth? And Galileo said, no, actually you wouldn't. Galileo invites us to consider the motion of a ship, and invites us to go down below decks, and in the cabin of the ship, set up a laboratory that we can do various experiments. We can toss objects in one direction or another. We can release flying animals and observe their motion. We can have a fishbowl and look at how the fish swim from one direction or another. And in this laboratory, if the ship is at rest, we observe how things move. We find it's no harder to throw a ball one direction in the ship than another, and so on. And now Galileo says, suppose the ship is moving uniformly over a calm sea. In that case, he said, we would not observe any difference in any of the experiments that we might perform in our laboratory. The laws of nature in our laboratory would look exactly the same as they would look for the stationary ship. No experiment inside the cabin of the ship can detect the uniform motion of the ship. And so, Galileo says, that's why we can't perceive directly the motion of the Earth through space. The next figure in our story is the great 19th century Scottish physicist James Clerk Maxwell. Now, Maxwell was the person who finally put together the theory of electromagnetism. And he showed that light traveled through space in the form of electromagnetic waves, oscillating electric and magnetic fields through otherwise empty space, moving at a speed c, 3 times 10 to the 8th meters per second, and the speed c is related to constants that have to do with electric and magnetic properties. And so from the electromagnetic experiments, you can determine the speed of light. But that raises the question. This is the speed of light with respect to what? And Maxwell thought he had the answer. Maxwell believed there was something called the ether. The ether was an all-pervading substance that filled space, even the apparently empty space between the planets and the stars. And this was the medium of the medium of electromagnetic oscillation. That light was a mechanical vibration of the ether. And he said, whatever difficulties we may have in forming a consistent idea of the constitution of the ether, there can be no doubt that the interplanetary and interstellar spaces are not empty, but are occupied by a material substance or body, which is certainly the largest and probably the most uniform body of which we have any knowledge. Now that raises the question. The Earth is not at rest through space. It's orbiting the Sun. Its motion around the Sun, its orbital velocity around the Sun is about 30 kilometers per second, which is about 1/10,000th of the speed of light. And so that means that the Earth is probably moving through the ether. And that means that if the speed of light is the speed with respect to the ether, then we should observe a different speed of light on the Earth if we shoot our light upwind or downwind, if you will. There's sort of an ether wind blowing through our laboratory. If we're shooting it with the ether or against the ether that's moving through our laboratory, we should see different speeds of light. Different speeds of light in different directions. Now, that's a tricky measurement to make, as Maxwell himself pointed out. The easiest way to measure the speed of light is to measure it on a round trip measurement, and that almost but not quite cancels out the effect. But the measurement is possible. Which brings us to the next step in the drama, which is the American experimentalist Albert Michelson. Now, Michelson had invented, as we've seen, a kind of interferometer, a fantastically precise device using interference between light traveling in different paths to measure the optical path length. And so we have a source of light, and then the source hits a half-silvered mirror. Some of the light is then transmitted, reflected from another mirror, and reflected again to a detector. Some of the light is reflected by the half-silvered mirror to another mirror and back again. And the two beams, the two paths that the light can follow, can interfere with each other at the detector, and the detector can see if it's constructive or destructive or something in between. Now, by setting up this interferometer and checking it at different angles, Michelson could detect very small variations in the speed of light in different directions. And he did this experiment in 1881, and then again with Edward Morley in 1887. And they found that there was no detectable ether wind. There's no detectable variation in the speed of light in different directions to a level of about 1 kilometer per second, only 3% of the orbital speed of the Earth. So this is a null result. There's no detectable difference in the speed of light in different directions, even though we're pretty sure that the Earth is moving around the sun. So how can that be? Well, lots of people had ideas about how to do this. Lorentz, Fitzgerald, Poincaré had all kinds of theories about why maybe this would not be observable. But the person who put it all together is Albert Einstein. We've all heard about Albert Einstein, and he's famous for many, many discoveries, but probably the thing he's most famous for is a paper he published in 1905 with the title On the Electrodynamics of Moving Bodies. So, what is it all about? Well, Einstein has a new way of looking at physics. It's a way that will solve the mystery of the Michelson-Morley experiment and preserve Galileo's idea that you can't detect absolute motion, and it will in fact preserve the mathematical form of Maxwell's electromagnetism. So, here's how it works. Einstein begins with two postulates. The first postulate says that the laws of physics are the same in every inertial frame of reference. And the second postulate says that the speed of light in a vacuum, that's c, is the same in all inertial frames of reference. Now, obviously, this brings up a couple of questions. First of all, what do we mean by a frame of reference? Well, a frame of reference is just a way of assigning space and time coordinates to events that happen in the world. It's often associated with a given observer, the frame of reference of an observer. We have a coordinate system, the coordinate system they would impose on the world around them. And what do we mean by an inertial frame of reference? Well, that's a frame of reference in which the law of inertia holds. That is to say, if you don't exert a force on a body, then the body stays at rest or in uniform motion. And that means that we aren't considering accelerated observers. If you're in an accelerated frame of reference, if you're in a car when you stomp on the brakes, then all kinds of things that nobody is pushing accelerate in that frame of reference. Things fall off the seat and so on. We're only going to be considering observers that are sort of moving uniformly with respect to each other. If they don't push anything, it doesn't move by itself, and that means that that we're considering what's called the special theory of relativity. To consider accelerated observers and so on in full detail, you'd need the general theory of relativity, but we'll content ourselves here with the special theory of relativity. To help us sort this out, let's introduce two observers who are in inertial frames, but they're different inertial frames of reference. Our first observer is Alice. Alice is operating in her own laboratory, which is aboard a moving train, a train that's moving uniformly down a long straight track. And we'll even imagine, since this is just a thought experiment, we'll even imagine that the train might move close to the speed of light. And then standing beside the track, observing the same phenomena in a different frame of reference, is Bob. Bob is at rest with respect to the track. He's not traveling along with the train. From Bob's point of view, Alice is moving at a speed v. But of course, from Alice's point of view, Bob is moving in the opposite direction at a speed v. For simplicity, we'll talk about the track as the x-axis, but of course it's the x-axis for Bob. We'll call it the x-prime axis for Alice, because Alice and Bob will have somewhat different coordinates, assigning space and time coordinates to the events. So Bob's coordinates we'll call x, y, z, and t, but Alice's coordinates we'll call x prime, y prime, z prime, and t prime. The primes mean, in Alice's frame of reference, the frame of reference that's moving along with the train. So to see how this might illustrate some of the perplexities of Einstein's postulates of relativity, let's suppose that Alice shoots an arrow in her train car, and the arrow moves at a speed, we'll call it u, from one end of the train to the other, and that's what Alice sees. Of course, from Bob's point of view, Alice is already moving at a speed v down the track. So what speed does Bob ascribe to the arrow? Well, common sense suggests that it's just the sum of the two, that the speed of the arrow is u plus v, the speed of the arrow relative to Alice plus the speed of Alice relative to Bob. And for slow speeds, that seems to work out pretty well. But as we'll see, this can't be exactly the correct answer at high speeds. Let's suppose that instead of shooting an arrow, Alice shines a beam of light. And the beam of light, of course, from her point of view, in her frame of reference, moves at a speed c. Light always travels at the speed c through a vacuum in every frame of reference. But what about Bob? Bob sees that Alice is moving at a speed v. Does this mean that he sees the beam of light move at a speed c plus v, since after all, Alice sees it going at a speed v, and c rather, and she's already moving at a speed v? And the answer is no. Somehow it must work out that Alice and Bob both see the light move at a speed c. So, to make that work is going to be a bit of a challenge. Alice and Bob are going to disagree about a lot of things. They're going to disagree about space measurements. They're going to disagree about time measurements. They're going to disagree about all kinds of things. Which things are moving, which things are at rest. They will agree about which things are actually accelerating, because they're both inertial observers. But there are three terribly important things that they will certainly agree about. And so let me mention those. The first thing they're going to agree about is the laws of physics. They will agree about the laws that hold for the particular physical situation that they're talking about, whether those laws are laws of mechanics or laws of electromagnetism or what have you. The second thing that they will always agree on is one of those laws, namely the speed of light in a vacuum. Any light beams that we look at moving through a vacuum will be moving at a speed c. And we'll actually use this fact quite a lot in figuring out the relation between Alice's frame of reference and Bob's frame of reference. And finally, and this is a subtle point, but we'll make use of it, they will agree about what events actually occur in the universe. They won't disagree about what happens. So, for example, if Alice sees the batter hits the baseball, Bob will not see that the batter misses the baseball. They'll both agree on whether or not the batter connects with the baseball. Okay, so armed with these 3 points of agreement, we can work out a lot of important stuff about the relation between Alice's frame of reference and Bob's frame of reference. That is to say, we can work out some things about the relativity in relativity. Let's consider another experiment involving Alice and Bob. First, we'll look at it from Alice's point of view. Now Alice has 2 flashlights pointing in opposite directions, and she's standing right in the middle of her train car laboratory. And she shines the lights at the same time. She presses the button on the lights at the same time at the same place, and the beams of light go out in the 2 directions at the same speed, c. And that means that they're going to reach the sides of the train car, the ends of the train car, at the same moment. You have 2 events, the beam of light reaching the left-hand side, the beam of light reaching the right-hand side. You have 2 events, and they happen at the same time. The events are simultaneous. But now, let's look at it from Bob's point of view. In Bob's point of view, the whole train car is moving. Nevertheless, the speed at which the flashlight beams travel is still c, the speed of light, in either direction. So when Alice turns them on, they go in each direction at the same speed, but meanwhile, Alice is also moving from Bob's point of view. And that means that the beam of light that's going to the right doesn't get out in front of Alice quite as much because Alice is following along, whereas the beam of light going to the left seems to separate from Alice more rapidly than C because Alice is going one direction and it's going the other. And so that means, since the end of the train car is approaching, that means that the beam of light reaches the left-hand end of the train car more rapidly, and that event happens first. And it's only much later that the other beam of light reaches the front of the train car, which is moving away from it, and that event occurs. So, from Bob's point of view, these 2 events, which happen at the same time in Alice's frame of reference, don't happen at the same time. They are not simultaneous. And this is an example of what's called the relativity of simultaneity. That's a fancy way of saying that events which are simultaneous in one frame of reference may not be simultaneous in another frame of reference. The concept of whether 2 events are simultaneous is a concept that depends on which frame of reference you're referring to. And from this we can draw a larger moral, namely that the time interval between 2 events may be different in different reference frames. In the case of the relativity of simultaneity, that time interval was 0 in Alice's frame, but was not 0 in Bob's frame. And that just means that it could be different. The time interval between 2 events could be different in Alice's frame of reference or in Bob's frame of reference. Not only can Alice and Bob disagree about the time interval between events, but they also might disagree about the distances, lengths of objects. All kinds of things might be different. So to help us sort out how things change and how things are the same, let's consider another interesting experiment. And let's imagine that there was a rule in relativity that said that moving objects get smaller, that they shrink in all directions. Distances are shorter for objects and frames of reference that are in motion. Can that work out? Can that be consistent? Well, let's imagine we have 2 meter sticks, and these meter sticks have attached to each end a paintbrush. And we'll call the meter sticks A and B for Alice and Bob, and these two meter sticks are going to fly past each other. Now, if let's first of all take a look at it from Bob's point of view. Alice's meter stick is moving, and if our pretended rule was true, if moving objects just simply shrunk, then Alice's meter stick would be shorter in this frame of reference. And what would happen? Well, as they flew past each other, the paintbrushes on Alice's meter stick would make marks on Bob's meter stick. But Bob's meter stick wouldn't make marks on Alice's meter stick because Bob's meter stick is too long. So a consequence of our rule would be a moving meter stick gets shorter. That means that that Alice's meter stick makes marks on Bob's meter stick. But suppose we look at the same thing from Alice's point of view. In Alice's point of view, it is Bob's meter stick that is in motion. And remember, Alice has to see exactly the same laws of physics that Bob does, and so Bob's meter stick must shrink. And then when Bob's meter stick flies past, it is actually Alice's meter stick that gets the marks of paint on it. Bob's meter stick doesn't. So which is it? Does Bob's meter stick get painted, or does Alice's meter stick get painted? And the answer, of course, is that both can't happen, and so neither one happens. The two meter sticks must look like they have the same distance, the same length, that is, in both frames. So how can we phrase this? Well, of course, in our example, we were moving the meter sticks perpendicular to their length. And so we can phrase this as saying one more thing that Alice and Bob must agree on. They must agree on, of course, the laws of physics and the speed of light in a vacuum and what events actually occur. In this case, which paint goes where. But they also must agree on lateral distances. That is to say, lengths that are perpendicular to the relative motion of Alice and Bob. Alice and Bob will agree on those lengths. They'll agree on those distances that are at right angles to the track along which Alice moves. And that's a very important, very useful, and kind of interesting point of agreement between Alice and Bob. We can use this fact about distances to tell us something important about time. So let's imagine a clock that we'll design to use light in its operation. We have a little box of electronics at one end, and then there's a pole, and on the other end we have mounted a mirror. And the mirror and the electronics box are a distance d apart. So here's how the clock works. First, the box emits a light flash. That's one tick of the clock. And then the pulse of light travels up to the mirror, and then reflects and travels back down to the electronics box, where it's received, and we have another flash caused by that flash, and that's the next tick of the clock. So how long does it take this clock to tick? What's the time between two ticks? The tick time, which we'll call delta t sub 0 because this clock is at rest, is 2 times the distance d divided by the speed of light. And if we could have other clocks sitting around this clock that operated in completely different ways, but of course all clocks kind of agree with each other. Clocks based on vibrating atoms or electromagnetic fields or springs or pendulums, they sort of all read the same kind of time, and so this clock would agree with the clock we built made from light. Okay, now let's consider the same clock, but consider it, suppose that it's moving to the right at a speed v. So initially, again, we have a tick of the clock, and the light flash is emitted, but of course the clock is moving. So when the light flash reaches the mirror has moved over a certain distance. And it reflects off the mirror, and then travels back down, and reaches the box of electronics, producing the second tick of the clock a certain time delta t later. The first thing I want to notice, just purely qualitatively, is that the light in this situation has traveled further. This is a longer distance because, of course, the lateral distance d is unchanged and the speed of light is unchanged. This is a longer distance, therefore a longer time. Therefore, this time to make one tick of the clock is longer than the time when the clock is at rest. This clock must be running slowly. Let's do the analysis. The total distance traveled is you can work out from the Pythagorean theorem, noting that the distance between the two ticks is just v times delta t, the tick time, and so you find that delta t is the square root of 2d squared plus v squared delta t squared all over the speed of light. So let's do the algebra. We have an expression for the tick time. The tick time's on both sides, so we square both sides, multiply both sides by c squared, and then we gather the terms involving delta t on one side, and we divide by c squared again. It turns out to be that's easy, and we find a relationship between the tick time and the quantity 2d over c, which was the tick time for the clock at rest. So that means that delta t is equal to delta t naught divided by this funny factor, the square root of 1 minus v over c quantity squared. In other words, the time that it takes for a moving clock to tick is indeed longer than the time it takes for a stationary clock to tick. Longer because that factor in the denominator is less than 1. Therefore, I'm sort of multiplying by a factor that's greater than 1. Now notice that this doesn't really have anything to do with the particular construction of the clock. We've used the properties of light to create this clock, but every kind of clock would tick in the same way as this kind of clock. So this fact that the moving clock runs more slowly must be a fact about every sort of clock, whether it's based on radioisotope decay or a vibrating spring or anything that you might imagine as a clock, an electric circuit. Every sort of clock, no matter what it's made of, no matter what physics goes into its construction, slows down by the same factor. This is the phenomenon of time dilation. A moving clock runs slowly. Now, to do it mathematically, we would give the expression we gave. We could write that delta t, the tick time for the moving clock, is a factor gamma times delta t naught, where gamma is what we'll call the relativistic factor. It's equal to 1 over the square root of 1 minus v over c quantity squared. That relativistic factor is going to show up a lot in relativity, so it's useful to give it its own name. Now, delta t sub 0 is special because that's the time it takes for the clock to tick in the clock's own frame of reference. So we call that the proper time. That's not proper in the sense of being better than some other time, but it is the time that's proper to the clock itself. So let's take a look at the behavior of this relativistic factor gamma. Let's graph it as a function of speed. If we graph this function, we notice that it starts out at 1, where v is equal to 0, gamma is equal to 1. And then as v gets larger, gamma begins to increase. It tilts up just a little bit. You have to be going pretty fast, though, close an appreciable fraction of the speed of light, before gamma is very much different from 1. And in ordinary speeds that we're familiar with, gamma is about equal to 1, which is why we haven't noticed in our everyday life that moving clocks run slow. When you approach the speed of light, though, the denominator of the gamma factor goes to 0. And that means that the gamma factor has a vertical asymptote at v equal to c. Gamma goes to infinity. So as a clock approaches the speed of light, it becomes very, very slow. The clock takes longer and longer and longer times to tick between as its velocity approaches the speed of light. You can get some qualitative idea by looking at this table of values for velocity and gamma. When velocity is very small, gamma is essentially 1. When you get up to about half the speed of light, or 9/10 the speed of light, or 99% of the speed of light, gamma becomes larger and larger and larger. The phenomenon of time dilation and the relativistic factor have a lot of really interesting consequences. For example, the muon is an elementary particle that is unstable. It decays into other particles. And it takes about 2 microseconds on average for the muon to decay into its products. And so it's not a very long-lived particle. But a fast muon lives longer because its internal clock is slowed down. So a muon that's moving at 99% of the speed of light, with a gamma factor of more than 7, lasts for 14 or 15 microseconds instead of only 2 microseconds. What that means is that at 99% of the speed of light, the muon can go a lot farther than you might expect, given its lifetime of its rest lifetime, its proper lifetime of only 2 microseconds. A lot farther than you might expect. And this is actually has a practical upshot. The cosmic rays at the top of the atmosphere produce muons. The muons come showering down. If it weren't for time dilation, though, no muons would reach the ground. It's just too far. It would take too long. But because of time dilation, these very, very fast muons live long enough to reach the ground. They still only live about 2 microseconds in their own frame of reference, but in the frame of reference of the Earth, they live for many, many microseconds. Plenty of time to get all the way to the ground. Now that we understand something about time dilation and a little bit about the relativistic factor gamma, let's think about the effect of motion on lengths. We know that an object that's moving doesn't change its lateral length, but what about its length in the direction of motion? So to analyze this, let's once again imagine Alice and Bob are next to each other. Alice is in her train car and Bob is standing next to the track. And let's imagine that Alice goes rolling past Bob at some speed v. First of all, we'll look at it in Alice's frame of reference. In Alice's frame of reference, the length of the train car is L sub 0. We'll call it L sub 0 means the length of the train car when it's at rest, and it's at rest with respect to Alice. And Bob is moving to the left at a speed v, and the amount of time it takes for him to traverse the length of the car is just what we'll call delta t sub a. That's the amount of time it takes in Alice's frame of reference, which is equal to L naught divided by v. Now, of course, if Alice is looking at Bob's watch to see how much time has elapsed on Bob's watch from as he passes the car, that time will be a little bit less because Bob's moving. His clock is running slowly, and so Bob's time, delta t sub b, will be Alice's time divided by the factor gamma. Divided by, because of course, in this case, it's Bob's time that is the proper time between the 2 ticks of Bob's clock. Anyway, that means that the elapsed time on Bob's watch will have to be L naught divided by gamma times v. It's Alice's time divided by gamma. Now let's look at the situation from Bob's point of view. Alice's train car now has a length L. We don't know from the outset that that's equal to the train car's length at rest. And it goes past Bob at a speed v. And that means that according to Bob, the time it takes is L over v. But that's equal to the elapsed time, remember, on Bob's clock that we already calculated. So L over v is equal to L naught over gamma times v. And if I just multiply both sides times v, I'll find out that L is equal to L naught over gamma. That is to say, the train car is shorter in Bob's frame of reference by the factor gamma. So what we found is what's called relativistic length contraction. A moving object is shorter along the direction of its motion. It's shorter by the factor gamma. L is equal to L naught times the square root of 1 minus v over c quantity squared, which is L naught over gamma. And L naught is the length of the object at rest, and so we'll call that the proper length, the length that's proper to that particular object, in its own frame of reference. Similar kinds of reasoning allow us to work out the relationship between the coordinates that Alice and Bob put on events in the world. Of course, Bob's coordinates are x, y, z, and t. Alice's coordinates are x prime, y prime, z prime, and t prime. But we can talk about how these coordinate systems are related to each other. And we can make a couple of assumptions to make things a little simpler. First of all, we'll suppose that Alice and Bob's coordinates agree on their origin point. That is, say at time equal to 0, Alice's origin and Bob's origin are in the same point. Alice and Bob are just passing each other at time equal to 0. And we'll also assume that Alice is moving at a speed v along Bob's x-axis in the positive direction. So those are the two simplifying assumptions we're making to put Alice and Bob's coordinates together. And these two coordinate systems are related by something called the Lorentz transformation, after Hendrik Lorentz, who did some work actually anticipating Einstein's work in relativity. Here are the equations for the Lorentz transformation. X prime, y prime, z prime, and t prime on the left-hand side are equal to expressions in terms of x, y, z, and t on the right-hand side. And so if we know the coordinates of an event, something that happens in Bob's coordinates, we can now work out the coordinates in Alice's coordinates. And I just want to point out a couple of things. First thing is to notice that the transformations are very simple for y and z. Of course, the directions perpendicular to Alice's motion are unchanged. The distances are unchanged in those directions. So those coordinates are unchanged. We also notice the relativistic factor gamma appearing in both the x transformation and the y transformation. And also in the x transformation, we notice that combination x minus vt. That just means that Alice's 0 point of her coordinate system is moving along the x-axis. And so what she calls x prime equal to 0 will be at different values of x at different values of time. So that sort of, you can see the Alice's coordinates shifting along the x-axis there. Of course, we could also write down transformation equations for Bob's coordinates in terms of Alice's coordinates. And they're very easy. It's very symmetrical. All you have to realize is that Bob is moving in the negative x direction at speed v. And so all you have to do is change where the primes are and replace minus v with minus v. And you get the Lorentz transformations for getting Bob's coordinates for space and time in terms of Alice's coordinates. Okay, so that's a first look at the ideas of special relativity that we'll be covering this week. Of course, we have a lot more to do in class. We want to look at what relativity has to say about how velocities combine. We want to say what relativity has to say about our ideas of energy and momentum and mass and their relationship with each other. Remember, relativity applies to everything. Relativity is a principle that all of the laws of physics ultimately have to subscribe to. We can often get away with ignoring it because at slow speeds the gamma factor is about 1 and the predictions of relativity are almost exactly the predictions of our familiar physics, the physics of Galileo and Newton. But when things are fast, things have high energies, we may need to think about relativity. So, there's lots more to do, and I'll see you in class.